In 2023, at a factory on the outskirts of London, an 18-story apartment block was quietly completed. No construction site noise, no dust clouds, no concrete mixer trucks rumbling through the neighborhood. It was finished in just 34 weeks. In most developed markets, a building of comparable scale would take a minimum of 2 years using conventional methods. So how is this possible? The answer comes down to two forces: artificial intelligence and modular construction. Today's video breaks down the economics of the era in which buildings can be stamped out like manufactured goods, analyzed from a practitioner's perspective. If you're an architect, a developer, or a contractor, this is what you need to understand right now. Modular construction still carries an outdated stigma in many markets. Think temporary site offices or prefab portacabins from the early 2000s. But that image no longer reflects the industry's reality. The global modular construction market stood at approximately $80 billion in 2024, with compound annual growth projected at 6.9% through 2030. Here is the core concept. Modular construction means completing 60 to 90% of a building, its structural frame, interior and exterior finishes, mechanical systems, and electrical wiring inside a factory. Then assembling the finished modules on site. Think of it as a Lego system for full-scale buildings. The critical variable is factory completion rate. The higher the completion rate leaving the factory, the shorter the on-site schedule and the tighter the quality tolerance. And the technology that dramatically raises that factory completion rate is artificial intelligence. AI touches modular construction at 4 distinct stages, and each stage compounds the value of the others. Stage 1. Design optimization. AI simulates thousands of module combinations simultaneously, optimizing for structural efficiency, thermal performance, and daylight access all at once. Work that would take a human design team months can be completed in hours. Notably, AI-powered design verification has been shown to reduce construction defects by approximately 41%, and AI drawing review tools can flag coordination errors in under 3 minutes, a task that can take a human reviewer an entire day. Stage 2. Manufacturing automation. CNC cutting, robotic welding, and automated finishing lines operate in sync through AI scheduling. Defect rates fall by up to 80% compared to equivalent on-site construction. Stage 3. Supply chain prediction. AI coordinates material procurement, logistics, sequencing, and module stacking order in real time, dramatically cutting inventory waste. Stage 4. On-site assembly management. Drones and computer vision detect assembly deviations to millimeter precision. When all 4 stages are integrated, manufacturing buildings at scale becomes a genuine operational model, not a theory. Now let's talk about money, the question every practitioner cares about most. Synthesizing global case data. AI-enabled modular construction reduces project schedules by an average of 40 to 55%, compared to conventional on-site methods. Once past the initial investment recovery threshold, cost reductions of 20 to 35% are achievable at scale. The labor dynamic makes the business case even stronger. Across developed construction markets, skilled labor costs have risen approximately 30% over the past 5 years. While chronic shortages of qualified tradespeople have become a structural problem, not a temporary one, this is exactly where modular's competitive advantage compounds. Factory production workers operate under standardized training protocols and have significantly lower turnover rates than site labor. Factory lines are also insulated from weather delays, neighborhood complaints, and nighttime noise restrictions. There is one non-negotiable condition, however: repeatability. Profitability in modular construction is driven by how many identical or near-identical modules can be produced from the same factory setup. High-mix, low-volume runs will not generate acceptable margins. Volume and standardization are the engine. So how should architects, interior designers, and contractors begin moving in this direction today? Standing up a dedicated modular factory from scratch is not a realistic first step. Here is a practical 3-stage entry strategy. Step 1. Build BIM capability first. Modular design starts with a BIM model at LOD 350 or above. This is the accepted global industry standard for factory-ready coordination. Get your teams fluent in module-level segmented design using platforms like Revit or ArchiCAD. AI design tools such as SpaceMaker and Hypar can be integrated at this stage for generative optimization. Critically, projects that adopt AI-powered BIM clash detection have seen an average 38% drop in requests for information, a direct measure of coordination quality. Step 2. Bring manufacturers into the design process early. Partner with established modular fabricators and structure the collaboration around design for manufacture and assembly, DFMA. The earlier a manufacturer's constraints are embedded in the design model, the higher the factory completion rate and the lower the on-site risk. Step 3. Target high repeatability project types. Student housing, assisted living facilities, logistics hub office modules, and workforce accommodation are among the fastest-growing modular segments globally. These project types share the standardization profile that makes factory economics work. Let's be direct about what is holding this back. In many markets, the first barrier is the regulatory framework. Building codes in most countries were designed around traditional on-site construction methods. When modules arrive from a factory 60 to 90% complete, it is often unclear which inspection standards apply, at what point, and who has jurisdiction. South Korea is a case in point. Its current Building Act creates ambiguity at the point of site delivery. And this is not unique. Regulators across Europe, North America, and Asia are actively working to close the same gap. The second barrier is upfront capital. Dedicated modular factory equipment and AI system integration require multi-million-dollar commitments before a single unit ships. This is difficult for mid-sized contractors to absorb alone and typically requires either government partnership or consortium models. The opportunity, however, is equally real. South Korea's government has announced a target to deliver 15% of new public rental housing through modular methods from 2025 onward, a signal consistent with public procurement shifts in the UK, Singapore, and Australia. Smart construction R&D budgets are growing for the third consecutive year. The firms that help define the standards during market formation will hold structural advantages for a decade. The window is open now. AI and modular construction are shifting the construction industry's fundamental paradigm from site-based craft knowledge to factory-based systems design. This transition cannot be stopped. The only variable is pace, how quickly the industry moves, and who leads. For architects and designers, the role is evolving. The profession is no longer solely about drawing buildings. It is increasingly about engineering production systems, systems that define how structures are specified, manufactured, and assembled at scale. Artificial intelligence sits at the center of that transformation. If today's video gave you a clearer picture of where this industry is heading, share your perspective in the comments below.